the temperature solution was this. So it's T hat equals C1 exponential of the square root of S over, is it alpha times X plus C2 exponential of minus square root of S over alpha times X plus T initial over S. Okay, that was the temperature expression. All we need to do then is to enforce our boundary condition in S, plug in this relationship. So we'd be saying basically that T hat is equal to T initial over S, which is equal to C1 times exponential of square root of S over alpha times X. But X is now infinity. So we have to write infinity here. And then same thing, so C plus C2 exponential of minus square root of S over alpha times infinity plus T initial over S. Okay, so if you're following this, you'll see the T initials over S cancel out. We see the second term. In the second term, let's see, this guy here. This one goes to 0, right? Exponential of minus infinity is 0. This term here does not go to 0. In fact, it blows up. So if we want a stable solution or we want a finite solution, we have to say C1 is 0. So out of this, we get C1 is equal to 0. And then we can rewrite our temperature solution to be T hat, again, we're still in the S domain, is C2 exponential minus square root of S over alpha times X plus T initial over S. Okay, so we're making progress there. We now have to do the second boundary condition, this one here. So let's skip forward. Again, I have an extra blank page here, so let's just move on to 1711. So in this one, we're going to take this boundary condition. We have to first take the Laplace transform of this thing. So doing that first, up here, we would have, I'll just write it out, it's going to be h bar times the quantity T initial over S plus beta over S squared minus T at X equals 0. It's equal to minus K dt hat dx at X equals 0. That was it. So hopefully we can see where this came from. This, right, is a constant, so the Laplace of that is the constant over S. Beta t, if you look at your table, that's going to be the constant over S squared. This just becomes T hat at X equals 0. This becomes dt dx at X equals 0 a hat, and then the constant comes along. So everything should be pretty straightforward just by looking at tables on that. No big issue there. Or you can just plug it into Maple, right? So we have that in the S domain. Again, we just have to enforce that boundary condition. So that's going to be as follows. We would say h bar times stuff that doesn't change, T initial over S plus beta over S squared minus, now we have to plug in our T hat and evaluate it at X equals 0. So that becomes C2 exponential at X equals 0, which is be exponential of 0 minus T initial over S. And that's all equal to, on the right-hand side, K times C2 times the square root of S over alpha exponential of minus square root of S over alpha times 0. Or just plugging in the stuff we know. Then we can simplify this, and it turns into h bar times beta over S squared minus C2 is equal to K times C2 times the square root of S over alpha. So keeping going on this, we can just solve this. So we'll solve this, and it becomes C2 equals h bar beta over s squared k square root of s over alpha plus h. So that's just, again, algebra there. So we solve for the second constant using our boundary condition on the convective side. So let's just rewrite what our solution is here. So it is now in the S domain, t hat is equal to h bar beta over s squared k square root of s over alpha plus h bar times exponential of minus square root of s over alpha times x plus t initial over s. Hopefully that's right. I think I said a. This is s over alpha, right? So okay, we have our Laplace transform now. We've enforced the boundary conditions. Everything is kind of set to go. The initial conditions already been set up for this. So what would come next, right? Or what is step 3? We got to get back to the time domain. If you go and look at tables, so let's look at the next slide here. If you go and look at tables, you will quickly discover that this will not work from a table perspective. And we can even, so like the problem is, okay, we have s squared, we have a square root of s here, so the constants are not really a problem, but you have, s to some funky power. What is that, 5 halves or something like that. You have another s up here in an exponential and a square root. And if you look over here, there's really not going to be a good option that matches that. So then the next thing we would do is let's go to Maple and try this. Let's see, Maple. So we go to Maple. Here we are. Let me make that a little bigger. Okay, so we will restart. We're going to load our library. And then this is, I think, what we had. It should be similar. So s squared, square root of s. Yeah, same thing. And then I'm going to just say, OK, I can't break this up further. Let's just try to solve it. And it's going to give me back this, which says, OK, I can pull some constants out. That's fine. The rest of it, I don't know. So it's saying like Laplace, this is just says, take the inverse of this, and that'll be your answer. Right? But that doesn't help us. So we're kind of stuck, right? Like this is OK, but this part is not. By the way, like this is the sign that something is not working. Is it just tells you, OK, yeah, go ahead and do that, right? But it doesn't give you anything useful. Yeah. So what we need to do then is we're going to go to the Talbot inversion and do it numerically. So let's look at that. Just make sure. OK. So we're going back to our example Talbot inversion. I believe this is the one we want here. So I'm going to come in and I'm going to code up that function in T of s. And it should look exactly the same. Here you see the square root of s over alpha, the s squared, so it looks pretty similar. T initial over s. It's the same function. My Laplace transform function, again, has to take s, and then it takes a bunch of other stuff that's related to my function that I need to evaluate it. So here I need a position, x, and then all these other constants. As far as this thing is concerned, I'm going to evaluate this at a given x. So x is basically a constant as far as this function knows. So here's the problem information. I'm setting up a time vector. That time vector, again, should not start at 0 because Laplace, inverse Laplace numerical approaches cannot evaluate it at 0. And we're going to go to, I guess, 200 seconds with 1,001 time steps. I'm going to evaluate this at these different x positions just so we can see what it looks like. And then down here, I'm calling this function up here at all these times at once for a list of all the x positions. So you just see here it's calling that function. I want to just comment on this number again. So one of the challenges with numerical, and Talbot's just one of a few in this family of numerical inversion. Any of these numerical inversion ones, what they're doing is taking a series, and just like the other series approximations we've done, where you take some number of terms and then you truncate it. Here it's doing the same thing. It has this kind of integral that it's trying to do, and it estimates the integral with this many terms. If you choose the wrong number, it's going to start, you make it smaller, it's going to have more error. If you make it too big, it's going to start becoming numerically unstable. And your solution actually kind of looks like it's random in some way. So the best way to choose this is one, just start with the default, but you can play around with it and try different values and see what happens. So that's kind of how you're going to want to deal with that. There's another, well, let's just do this first and I'll give you other caveats. So let's run this, and here we are. So here we see at different x positions, so x equals 0 is right on the convecting surface. And then as you go further in, you go higher x. So we're seeing ramping up of temperature. There's this initial kind of transient thing, and then it follows along. We would kind of expect that. The temperature in the T infinity is going up linearly. So eventually we'd expect to see the temperature following along linearly on the surface. But then we see this kind of delay. We'd expect this delay as you go further in, that it takes longer for the material to respond. Right? So it kind of makes sense what we're looking at here. This is temperature as a function of time. Right, so Laplace inverse using the Talbot inversion is happy to deal with this. So this is a really powerful way of doing things, but there are some limitations. One limitation was the number of terms that I showed you. The other thing was, if we go back, let me just flip back here for a second. So if we look at these equations here, if you have a circumstance in which one of your functions in S has something like this in the denominator, particularly like a sine equation or cosine, something that's oscillating, and you see that there's S squared or whatever, S and something else, there is a condition. S can be positive or negative, and in the numerical approach for inversion, it's actually a complex number. So as you're taking the square of that complex number, you can still have a negative component to it. So at some point, there is a condition at which S squared plus C squared is going to equal 0. All right? And you get a discontinuity. You get the solution actually blows up. So when you're using the numerical inversion techniques, you need to watch out for something that kind of looks like this. So if we can draw, you'd have your solution going along in time, and maybe it looks. So I'll give you a hint on the homework. Your solution is probably going to look something like this. All right, you have this kind of oscillating thing. If you go far enough out in time, this S is going to eventually intersect with the complement and cause the function to fail. And your solution would kind of do something like this. It would go, oops, not that, it would do this. It'd go like this. You get this kind of jolt, and then all the oscillating stuff goes away. So what that's telling you is your solution is only valid up to this point. Anything to the right of that, you're now not doing part of the numerical integration is not complete. So watch out for that. You're going to only be able to simulate up to some intermediate time. You can't just go out indefinitely. Okay? So the solution, if you see this in your solution, it's a hint that something's different from what I intended. I have the solution going up to a point before this, so you shouldn't see it, but you might if you made an error. Okay, so that's, I guess, the overview of Laplace 1D. Any other questions on this before? Yeah.
So is there a way to know when you reach that critical, like before you even implement your numerical inversion, to that critical time where it will just
Yeah, that's a good question, and I was actually trying to figure that out before talking about this. As far as I got was, because it's a complex number, and because all the parameters sort of feed into what the value of S is that you're choosing, it's not straightforward to analytically solve for which complex value of S is going to be problematic. So what is typically done, as far as I can tell, is that people will just numerically root find to find the problems and then say my solution's up to this point. But the real hint is, like, you look at this and you see this kind of weird behavior. That's your sign that you're hitting that inflection point and you're done.
So if some of these can't be solved analytically and then they can only be solved numerically, but then they might also have like a discontinuity, is there any other like method out there to like solve past it, or is that where it's used?
Yes.
For an experiment?
Yes. So we would be. This is still let's say it's an analytical representation in the Laplace domain with a numerical integration or a numerical inversion. So it's still this sort of pseudo-analytical approach. You can just do purely numerical, and we'll talk about that next, right? You can just do the same thing we did for other numerical solutions where you discretize into nodes and do resistance formula and stuff like that. So, and that's a great segue for what we'll be doing next. Yeah. Other questions on this? Okay. All right, so let's see what happens. So if we plotted out, we had decided that we could try to predict the behavior. If you plotted it out on a log scale, this was our prediction, based on some of the relationships, and you plot it out, and it actually kind of looks like that. So just validating that our intuition about this problem was kind of right.